Example 16.7, brightness of bulbs connected in parallel and in series is on page 600. It says, assume that we have a battery and two identical light bulbs, each of resistance R. We connect the bulbs to the battery in three different configurations. One bulb, which is A, two bulbs in series, which is B, or two bulbs in parallel, which is C. Determine the equivalent resistance of a single resistor that will produce the same current through the battery as produced in arrangements B and C. Next, compare the total power output of the bulbs and arrangements B and C with the output in A. These three pictures will come back. If you didn't get a chance to get them written down, that's okay. So first, you're going to draw the three arrangements, and then we'll use equivalent resistance, which we had in the notes, and then we're going to use Joule's law to determine power. Assume that the connecting wires and the battery are not affecting anything. We'll say the bulbs are identical, that they're ohmic, and I guess that's all I'm going to put there. For resistors in series, so equivalent resistance in series, oh man, that would be equal to R plus R. So if I were to say what the equivalent resistance is in circuit B, you would say, well, that's equal to 2R. For parallel, it's a little more difficult. Equivalent resistance parallel is equal to 1 over R plus 1 over R to the negative 1, or the inverse of that. So if you had 1 over R plus 1 over R, if you have 1 over R plus 1 over R, that's going to be equal to 2 over R, but it's to the negative 1, or inverse, so that's equal to R over 2, or half of the resistance. So we're going to keep these two things in mind when we're talking about equivalent resistances. As far as how do they relate to current, well, Ohm's law, current is equal to the potential difference, or the EMF. In this case, we're saying the battery has very little resistance, so we can consider it just EMF, over the equivalent resistance. For power, we'll be using power is equal to current squared times our equivalent resistance. And we're going to look at each of these three situations individually using these things. So for our first circuit that has one bulb, we would say that our current for one bulb, is equal to our EMF over our resistance. Just Ohm's law, simple circuit, pretty straightforward. Our power for one bulb is equal to our current squared for one bulb times the resistance. Because I said over here, oh boy, that changed a lot. Because I said over here on the left that current is equal to EMF over resistance, we could take EMF over resistance and put it in here for current, so that we're just relating it to EMF and resistance. So, come back, here we go. So our power could be equal to EMF over resistance, but it's squared, times resistance. So EMF on the top is going to be squared. Resistance on the bottom is going to be squared, but we're also going to have another R that will cancel one of those R's. So our power for one bulb is equal to our value for EMF squared over resistance. For the next two circuits, we're going to keep relating back to these two things. That for one bulb, we're comparing the current of one bulb and the power of one bulb to these two other circuits. The current of one bulb is EMF over resistance. The power for one bulb is EMF squared over resistance. And I'm going to keep coming back to these. Pause. Pause. Except for it won't let me pause. So I guess we're going. We're just going to go. All right. Fair enough. So for B, now we've got them in series. So our current for series is going to be equal to our EMF. Well, it looks like I have an upside down heart on it. Over our equivalent resistance for series. If I go back to find out what was my equivalent resistance for series, if I had two resistors together that were equal, it was 2R. Okay, I'm going to go back. So I could say that for our series, it would be EMF over 2R. And since I want to compare this back to the one bulb system, I'm going to keep going back to it. One bulb, the current of one bulb was E over R. So the current of two bulbs in series would be 1/2 the current of one bulb. Or actually, I won't even need that parentheses. 1/2 of the current of one bulb. We're going to keep comparing to the original one bulb. Close enough. As far as power in series, so power in series is equal to our current squared in series times our equivalent resistance in series. I just put this in for my current in series. I can actually take that current and double it. Actually, but instead, since I want to take this back to EMF and resistance, I'm going to take this. EMF over my equivalent resistance is equal to the current in series. So E over R equivalent for my series it says series. You don't believe me? Too bad. So that's got to be squared times the equivalent resistance in series. You could distribute those as you do. Ooh, one thing I do need to mention. Our equivalent resistance in series. Equivalent resistance in series was 2R. So I can have this value equal to 2R. So E over equivalence in series, 2R. Those are both going to be squared. Extendo, extendo. Now I can distribute that square. I get E squared over 4R squared times 2 times R. Obviously, there's some canceling that can happen. I can get rid of that. I can get rid of one of those. 2 over 4, that's the same as 1/2. 1/2 E squared over R. 1/2 E squared over R. Relate this back to the power of one bulb. What was the power of one bulb? It was E squared over R. Okay. E squared over R. So this ends up being the power in series ends up being 1/2 the power of one bulb. Okay, one more to do. That's the parallel resistance. Compare these back to our original bulb. So our current in parallel. Ooh, that's not good. Oh, it's even not gooder. P-A-R-A-L-L-E-L. Parallel is equal to our EMF over our equivalent resistance in the parallel circuit. If I relate this back to, yet again, our equivalent resistance in parallel. What was that? What was that? What was that? What was that? That was R over 2. So, move forward, extendo pageo, is equal to my current in parallel. If I do some rearranging, let's see. Well, if I could relate, I have to relate this to the current of the one bulb system. What was the current of the one bulb system? It was E over R. So how does this relate to E over R? Pretty closely. Divided by 2 puts 2 on the top, so 2 times. And I said the current on one bulb was E over R, so 2 times the current on one bulb by putting them in parallel, equivalent current in parallel. Ooh, that's pretty nasty, but it'll work. Power, last one, comparing our power in parallel to our power for a single or a one bulb circuit. So power and in parallel, I'm just going to do that. That's way easier. Is equal to I squared in parallel times equivalent resistance in parallel. Well, relating the EMF and R, right here, I have that my current's equal to this. My parallel current is equal to EMF over R over 2. So really 2 times E over R. But that whole thing's going to have to be squared. Our equivalent resistance in parallel. I said that earlier. Equivalent resistance in parallel was R over 2. So I can say R over 2. I can distribute out the square. So I've got 2 times 2, or 2 squared, not 2 times 2. 2 squared is 4. E squared, R squared times this value R over 2 is equal to my parallel power. We're going to have some canceling happening like crazy. One of the R's can go away. 4 over 2, that sounds like 2 to me. 2 times E squared over R. I want to relate this back to the power of one bulb, which was E squared over R. Here I am at 2 E squared over R. So I am using 2 times the power of one bulb. Ooh, that's a B. That's a lot. That's a lot. what do we learn from this? All right, so if we have one bulb system, we have a current, we have a power. If we take those bulbs and put them in series, our current in series is half of what it would have been in one bulb. And our power is half as it would have been in one bulb. In parallel, we have twice the current as in a one bulb system and twice the power.